In section 7.1, we learned all about functions. And in section 7.2, we're going to learn about a lot of the properties of functions. So in this section, we are examining two important properties that functions may satisfy. The property of being one-to-one and the property of being onto. Functions that satisfy both properties are called a one-to-one correspondence, or often what I like to call them is a bijection. So we call them bijective or a one-to-one onto function. And when a function is a one-to-one correspondence or bijection, the elements of its domain and codomain match up perfectly, and we can define an inverse function from the codomain to the domain that sort of undoes the action of the function. Think of this as the kind of inverses you've learned about before. So the cube root of x can be undone by cubing x. If x is squared, we can undo it with a square root. Those are the ideas of the inverses here, undoing one another. So in an arrow diagram, if no two arrows that start in the domain point to the same element of the codomain, then our function is said to be one-to-one or injective. And I will say I tend to use one-to-one and onto rather than injective and surjective, but I do use bijective. So for a one-to-one function, each element of the codomain is the image of, at most, one element in the domain. So what does this look like? We define this officially informally as f is the mapping from x to y, and it is one-to-one. If and only if, for all x1 and x2 in the set of x, which is our domain, if f of x1 equals f of x2, then x1 has to equal x2. This is going to become very important when we start writing proofs of functions being one-to-one. It means that if I have the same output value, my input needs to be exactly the same. If I put in 2 and get out 4, every time I put in 2, I better get out 4, and I better not be able to put in any other kind of value for x and get out 4 as a result to my function. That's what it means to be one-to-one. So based on what we know of negations, how could we negate this function? Well, let's think about it. We have a function that says f, the mapping from x to y, is one-to-one. So let's negate that by saying f, the mapping from x to y, is not one-to-one. 2, 1. If and only if, instead of for all, it becomes there exists x1 and x2 in our domain x, such that, remember if and if then a conditional, when it's negated becomes an and. It was p and not q, so it'd be such that f of x1 equals f of x2 and x1 does not equal x2. So that's how we can determine if a function is not one-to-one. Let's look at an example. So are either of these functions one-to-one? We want to justify our response based on the definition of one-to-one, which I'll leave up at the top. So if we look at our first function, we notice that A maps to W, B to V, C to X, and D to Y. So is this function one-to-one? Well, that answer is yes. So f, our function f here, is one-to-one because no two elements in the domain x map to more than one or are sent by f to the same element in our codomain y. So no two x's map to the same element in the codomain y. That's the more informal way to say it. So if we look at G instead, we notice that it's a little different because A maps to W, B to U, but C also maps to W and D maps to Y. So this function is not one-to-one. So G is not one-to-one. because elements A and C, so elements A and C that are in our domain X are sent by G to the same element W in our codomain Y. The quick way of saying is that G of A equals G of C, and they both equal W. So those ones we had arrow diagrams. What if we don't have an arrow diagram? Can we figure it out? Well, let's see. In example 7.2.2, we say, let X, our domain, be the set 1, 2, 3, and Y, our codomain, be the set A, B, C, D. We want to define function h that maps from x to y as follows. H of 1 is equal to c, h of 2 is equal to a, and h of 3 is equal to d. We want to define our function k as the mapping from x to y as follows. K of 1 is d, k of 2 is b, k of 3 is d, and is either 1, 1 to 1. Well, let's start with h. So h, see here, h is the mapping here. It says that h of 1 is C, h of 2 is A, and h of 3 is D. So is h 1 to 1? The answer is yes, absolutely. H is 1 to 1 because each of the elements in the domain X is sent by H, by H to a different element in the codomain Y. If we were to write them out as ordered pairs almost, kind of like we were defining a function, we would say h of 1 doesn't equal h of 2. H of 2 does not equal h of 3. And h of 1 does not equal h of 3. H of 3. So none of our functions valued at each element in the domain is equal to any other function's value in the domain. For the same reasons, K is not 1 to 1 because K is defined as K of 1 is equal to D, K of 2 is equal to B, and K of 3 is equal to D. So we have two different values, our two input values that have the same output. Our inputs 1 and 3 both have the same output value D. So we would say K is not 1 to 1 because elements 1 and 3 in our domain X, don't mind the page number there, are sent by H, or sorry, in this case K, are sent by K to the same element D in the codomain Y. In other words, if we wrote it out the same way we did before, K of 1 equals K of 3, which is equal to D. But 1 doesn't equal 3. The next question is, how can we write a proof for a function being 1 to 1? Well, you knew proofs were coming in again. So to prove that a function f is 1 to 1, we will use the method of direct proof, as we have in almost all of our proofs. So we're going to suppose x1 and x2 are elements in our domain X such that f of x1 equals f of x2. So we are going to suppose all of that, and then we want to show that x1 must equal x2. So to show that a function f is not 1 to 1, we would find elements x1 and x2 in our domain such that f of x1 equals f of x2, but they're not the same value, so x1 does not equal x2. So let's look at our first example. It says, is the function f that maps from real to real with f of x equal to 4x minus 1 for all x in the set of real numbers 1 to 1? Prove or give a counterexample. Well, let's start with our statement. Start our statement by saying, for all x in a set of real numbers, if the function f, mapping from real to real, is defined by the rule, and then we'll state what f of x is, f of x equals 4x minus 1, then f is 1 to 1. So our proof, we already saw above, we're going to get to suppose x1 and x2 are in our domain. Our domain here is all real numbers. And remember, if you don't have explicitly stated what our domain and codomain are, they are given by our function mapping from our domain to our codomain. So our domain here is real, our codomain is also all real numbers. So we're going to suppose that x1 and x2 are elements in a set of real numbers such that f of x1 equals f of x2. And then by the definition of f, we're going to plug each one in. By the definition of f, f of x1 equaling f of x2 means that, well, take f of x and change x to x1. We get 4 x1 minus 1 equals, now change it to x2, 4 x2 minus 1. If we add 1 to both sides, we end up with 4x1 equals 4x2. When we divide each side by 4, we get x1 equals x2. So therefore, by the definition of 1 to 1, f is 1 to 1. These will probably be your favorite proofs from this section. They're super quick, super straightforward. You plug in f of x1 and f of x2. The only time really that we're going to find a problem with showing that it's 1 to 1 is if we have an even polynomial, an even degree of a polynomial, because then you could have plus and minus roots and things like that, and plus and minus values for x. So that's the only time, and in fact, we're going to see that on the next example. Because our example 7.2.4 says, is G the mapping from integer to integer? So our domain and our codomain are both a set of integers with G of n equal to n squared. Notice that's that even degree that I mentioned before for all n in the set of integers. Is it 1 to 1? Prove or give a counterexample. So in this case, we'll still write our statement. Our statement will say for all n in the set of integers, if G, the mapping from z to z, is the function defined by the rule G of n equals n squared, then G is 1 to 1. And there are a couple of ways we can go about this. We can either disprove it or we can give a counterexample. And in this case, I gave a counterexample. So I'm going to call it counterexample so you know exactly what I'm doing instead of calling it proof. If I let n1 equal 1 and n2 equal negative 1, we know that n1 and n2 are integers. Then, by the definition of G, G of n1 equals 1 squared, which is 1, and G of n2 equals negative 1 squared, which is also 1. Hence, G of n1 equals G of N2. However, N1 does not equal N2. So therefore, by the definition of 1-to-1, G is not 1-to-1. So we saw one example of G being 1-to-1 and one example where G is not 1-to-1. And next we're going to move into the definition of onto. So we learned in section 7.1 that we can have elements in the codomain of a function that are not in the range of the function. We also learned that it is possible for every element in the codomain to be an inverse image of some element in its domain. The latter is called onto or surjective. And again, like I said, I use 1-to-1 and onto, but I will use bijective for functions that are both 1-to-1 and onto. You can use injective and surjective. It just takes me a minute to think about which one is which. So when a function is onto, its range is equal to its codomain. So formally that says the function f that maps from x to y is onto if and only if there exists some y in our codomain, or sorry, for every y in our codomain, there exists some x in our domain such that f of x equals y. Meaning that every element in our codomain is being mapped to by our function. So based on what we know about negations, let's negate this. We would say that f is the function that maps from x to y is not onto if and only if there exists some y in the set of big Y, some element y in the codomain, such that for every x in our domain, f of x does not equal y. So in other words, there is an element in our codomain that even if we looked at every single element in our domain, not one of them will map to it. Not one of those elements is sent by our function f to that element in the codomain. If we find even one element in the codomain that is not being mapped to by our function is not onto. Let's try our hand at determining whether a function is or is not onto. Let's look at the first one for f. 1 maps to A, 2 to C, 3 to C, 4 to D, 5 to D. So this is definitely not 1-to-1. It also is not onto because element B in our codomain is not being mapped to. So F is not onto because element B in our codomain has no inverse image in X, image in our domain X. So B doesn't equal f of x for all x in our domain. That's what it means. So this function, this f is a function. Yep, it is a function. And it is not 1-to-1. And it is not onto. So it's just a function. Well, what about G? G is a function, right? And we have 1 maps to B, 2 to C, 3 to A, 4 to C, and 5 to D. This is definitely a function. It is not 1-to-1, but it is onto because every element in our codomain, A, B, C, and D, all have arrows coming into them. They are all the inverse image of some element in our domain. So we would say here that G is onto because for every element in our codomain, it has an inverse image in the domain X. And if we state it like we did before, we would say A is equal to G of 3, B is equal to G of 2, C is equal to G of, let's see here. Oh, I think C, did I mark them down wrong? Let's see here. A is G of 3, B is G of 1. That's where I messed up. Let me go fix that. That's G of 1. I get to talking and writing and write the wrong thing. So A is mapped to by 3, B is mapped to by 1, and C is mapped to by both 2 and 4. So C is equal to G of 2 and G of 4, and D is mapped to by 5. So D is G of 5. And you know, of course, that we're going to have to learn how to write proofs with onto as well as one-to-one. And then we're going to do both together to show that a function is bijective. So how do we go about proving that a function is onto? Well, we're going to use our method of generalizing from the generic particular, meaning we're going to suppose that y is any element in our codomain, and then we will show that there is an element x in our domain such that f of x equals y. To show that a function f is not onto, we can find any element in our codomain such that it does not equal f of x for any x in our domain. So much like before, we're going to look at two functions, one where it is onto and one where it is not. So we can try to understand what it means to have and to not have a function that is onto. So let's look at example 7.2.6. Is f the function that maps from real to real, so domain and codomain are both all sets of all real, with f of x equals 4x minus 1 for all x in our set of reals onto? Prove or give a counterexample. Well, let's start with our statement. And these statements are usually the longest things in these proofs. So for all x in the set of real numbers, if f, the mapping from real to real, is the function defined by the rule f of x equals 4x minus 1, then f is onto. And let's start our proof. Our proof says, suppose that y is any element in our codomain. Okay, well, we're going to suppose y is in the set of real numbers. And we're going to define an x value. But in order to define that x value, we need to figure out what x value we want here to define all of our mappings. So let's think about it over here with our scratch work. This is our scratch work. It's not part of our formal definition here, our formal proof, but we need some scratch work. So to find that value of x that we can use defined in terms of y that would work for every y, we're going to use this concept of inverses. So we're going to say y equals 4x minus 1, and we're going to find its inverse. We're going to solve for x. So add 1 to both sides, so y plus 1 equals 4x, and then you can divide both sides by 4. So y plus 1 over 4 is equal to x. So we're going to let x equal y plus 1 over 4. And why would we want to do that? That seems like an odd thing to say, right? Well, then we know that x is a real number because real numbers, and this is where you have to think about it, real numbers are closed under. Well, we already know that sums, differences, and products of real numbers are real numbers. But what else we're going to say now is we're going to add a little bit more to this. So we are only using sums here. So an addition and a division. So x is real because real numbers are closed under addition and division other than by 0. Other than by 0. So why can we do this with reals, but we can't do it with other kinds of numbers? Because the only exception to the division rule with real numbers is 0. Any of our other numbers, we have a long, infinite list of numbers that would create a problem. Lists and lists and lists, an infinite number of combinations that would give us problems. But with real numbers, think of these like your floats when you're programming. You can divide a float by a float, a real number by a real number, as long as you're not dividing by 0, you are 100% okay. You will always get a real number back. You'll get a float back. That's the idea here. So we just showed that x is in our domain. That's what we were trying to do. So now we've defined an x that is in our domain. So then we know that we need to define f of x. So we will say it follows that f of x is equal to f of this new x that we just defined, which is y plus 1 over 4. And we then know that that is, when we plug it back into f, will be 4 times this x, which is y plus 1 over 4, minus 1, which is 4 times 4 is just 1, so we get y plus 1 minus 1, or y. And that was what we were supposed to show. We wanted to show that there is an element x in our domain. Well, we showed that it was in our domain, such that y equals f of x. And we just did. F of x is equal to y. So therefore, I kind of ran out of space. So therefore, by the definition of onto, f is onto. But what would it look like to have a function that's not onto? That's what we're going to look at example 7.2.7. This one took the same function, but instead we're limiting ourselves to only being in the domain and codomain that are all integers. So we're letting new function h be the mapping from integer to integer, so codomain and domain are both integer, with h of n equal 4n minus 1 for all n in the set of integers. Is it onto? Well, that means, remember, that every value in our codomain must be mapped to, every integer must be mapped to by this function. And we can try it by just trying to write a proof the normal way, and we'll see something interesting will happen. So let's try that. So let's write our statement. So for all n in a set of integers, if h of n, if h, the mapping from z to z, is defined by the rule h of n equals 4n minus 1, then h of n is onto. And let's try to write our proof and see what happens. So we're going to suppose y is an integer. And this time it's going to be n, not x. So we'll say n equals, and because we're using the same function as before, we can use that same inverse as before. We'll just say n is y plus 1 over 4. Same scratch work as before. Then, what do we know about n? Is n an integer? Well, not really. We know n is rational, right? It is an integer over an integer, so it's rational. However, not all rational numbers are integers. So you could say something along those lines. Or you could say, then n is not an integer because integers are not closed under division. Either one of these would work. I'm going to scroll it up just a little bit. You could use, these are just different options. So here would be, this would be option 1, and this one would be option 2. There are 2 different ways here that you can disprove. So here's option 1, option 2. You don't want to use both, just use one of them. Or you could say n is a quotient and not all quotients are integers, or you could say that n can't be an integer because integers are not closed under division. And I had forgotten to cross out the is an element of, so it can't be an element in the set of integers. So therefore, by the definition of onto, right, then here h is not onto. And that would be it. If you really wanted to, you could also use a counterexample. If you wanted to go the counterexample route, well, let's see here. Another option would be the counterexample here. So if you wanted to go to counterexample, we would say let y equal 0, and then we know that 0 is an integer. Okay, so then y is an integer. Okay, that works. Then we would say then h of n must equal 0. And by the definition of h, we would say then that 4n minus 1 has to equal 0, or 4n has to equal 1, or n equals 1/4. But this is going to be a problem because is 1/4 an integer? The answer is no. We would say, however, right? However, 1/4 is not an integer. So hence, there is no integer n such that h of n equals 0. And therefore, by the definition of onto, h is not onto. So you have lots of options when it is not onto. And the best suggestion I can do here is, as I can tell you, is just go ahead and solve for x or n and plug it in and see if it fits the right domain. If you don't get the right domain, then you know that your function is not onto. That's the best suggestion I have for you in these cases. You'll get better at it the more you do it. Usually you'll find out that it's when we limit ourselves to a domain or a codomain that is a set of integers that we have issues. So I've mentioned bijections a few times already. So let's define one officially. So let's consider the function f that maps from x to y that is both one-to-one and onto. It's both injective and surjective, respectively. Then the injective and surjective functions set up a pairing between the elements of x and the elements of y that matches each element of x with exactly one element in y, and each element of y with exactly one element in x. Such a pairing is called a one-to-one correspondence or bijection. So a bijection from a set x to a set y is a function f that maps from x to y in such a way that f is both one-to-one and onto. So here's a quick, easy arrow diagram to show it. Each element in the domain X is mapped to each element in the domain F, 1 to 1. Each X is mapped to only one Y. Each Y is mapped to by only one X. That is what a bijection is. That is what a one-to-one correspondence is. So for each of the arrow diagrams below, we have to decide if it is one-to-one, onto, both, or neither. And yours have them drawn in already. So I'm going to go grab those and I'll be right back. All right, now that I went and grabbed those pictures that you guys have on your notes that I apparently forgot to bring in with mine, let's look at these functions. For the first one, we have a function f that maps from domain x to codomain y, such a way that a, b, and d all map to 1, and c maps to 2. So is this function one-to-one? Is it onto? Well, the easiest one to pick out first is it is not onto because element 3 is not being mapped to. So this is not onto. Is it one-to-one? Well, no, because elements A, B, and D all map to the same element. So this is not one-to-one. So this is a function, it's just not one-to-one, nor is it onto. So this would be neither. Neither one-to-one nor onto. And there may be a question on the homework that's similar. Let's look at G. Is G one-to-one? And that answer is yes, G is one-to-one. So let's write it in. G is a one-to-one. But the question now remains, is G onto? And that answer is no, because the element in our codomain 4 is not being mapped to, so it is not onto. How about H? Is H one-to-one? And I hope you said no, because B and D are mapping to the same element in our codomain, so it is not one-to-one. Is it onto? And the answer is yes, every element in our codomain is being mapped to, so it is onto. So we've seen one function that is neither, one function that is one-to-one, and one function that is onto, so you can guess that the last one is going to be both. And that's the case. Every element in our domain maps to only one element in our codomain, and every element in our codomain is being mapped to, so this is a one-to-one correspondence or a bijection. So this one is one-to-one, it is onto, and therefore it is a bijection. So this one was one-to-one, this one was onto, and this one was neither. So these arrow diagrams make quick work of figuring out whether our function is one-to-one, onto, or a bijection. So the last thing we're going to cover on functions before we move into inverses is we're going to talk about proving that a function is bijective. So is f the mapping from the real to real, the function, with the rule f of x equals 2x plus 3 for all x in the set of reals, a bijection? So here's the thing. For these ones, we are going to have to prove, much like with our set proofs, we had to prove subsets both ways. For a bijection, we have to prove that our function is both one-to-one and onto. So we will write one statement. We will say for all x in the set of real numbers, if f is the function mapping from real to real, is the function defined by the rule f of x equals 2x plus 3, then f is bijective. You can also say is a bijection, is a one-to-one correspondence. Any of the above terminology would be absolutely fine. So our proof is we're going to suppose that f is the function, f, the mapping from real to real, is the function defined by the rule f of x equals 2x plus 3. So we're going to assume so. So we're going to assume x is a real number such that, oh, here we would say for our real number x. So we're going to suppose that x is a real number such that f is the mapping from real to real, is the function defined by the rule f of x equals 2x plus 3. So in other words, we're supposing that the hypothesis is true in our conditional statement. No different from any other kind of direct proof before. The way that we're going to prove that our function is defined by this rule, and this rule means that it is bijective, is to prove that f is both one-to-one and onto. So if you remember, one-to-one is the easy one. So one-to-one, we will say, suppose x1 and x2 are in our domain, which is the set of real numbers, such that f of x1 equals f of x2. Well, then by the definition of f, we can say then that f of x1 equaling f of x2 means that we have 2 times x1 plus 3. So 2x1 plus 3 equals 2x2 plus 3. Subtract 3 from both sides, so 2x1 equals 2x2. Divide both sides by 2. We get x1 equals x2. And therefore, by the definition of onto, oops, sorry, not onto, I keep saying the wrong one. Definition of one-to-one, f is one-to-one. So we just showed that f is one-to-one. Now let's see if we can show that f is onto. So we're going to let y be a real number because it has to be in our codomain. And remember, we have to solve for x again. So let's see if we can figure out what x is. So here's our scratch work. So we're going to say y equals 2x plus 3. So y minus 3 equals 2x. And y minus 3 all over 2 then equals x. So we're going to say, and let x equal y minus 3 over 2. Then we know that x is a real number because real numbers, real numbers are closed under, well, here we have subtraction and division other than by 0. Other than by 0. All right, so it follows that f of x here, let's see if I think we have space, f of x is now going to be f of, well, that x that we just came up with, which is y minus 3 over 2. And the goal, remember, is to get it to churn out y in the end. When we plug that into 2x plus 3, we get 2 times this y minus 3 over 2, right, plus 3, which is then y minus 3 plus 3, or just y. And that's exactly what we were looking for. So therefore, by the definition of onto, f is onto. And now that we've shown that f is both one-to-one and onto, we know that f is bijective. So we would say it follows, or hence, how about this? We'll say hence, f is bijective because f is one-to-one and onto. And that is our full bijective proof. And that is the last proof we're writing in this section. The last topic we have in this section is on inverse functions. So what are inverse functions? Well, you've talked about inverse functions in your prerequisite courses. You've talked about them in pre-calculus, you've talked about them in calculus, you've talked about them in several places, and this is not really any different of an idea of what an inverse function is. We're just giving it a very formal definition. So if f is a bijective function from set x to set y, then there is a function from y to x that undoes the action of f. This function is called the inverse function. F inverse, which maps from y back to x, and it sends each element in y back to the element in x that it came from. So officially, F inverse of y equals x if and only if y equals f of x. So again, same inverse function you've always learned about. We're just giving it a very, very formal definition. So it follows easily from the definition of an inverse function and bijection that if a function is bijective, its inverse function is also bijective. And the arrow diagram below illustrates the fact that an inverse function sends each element back to where it came from. So if we have x is equal to f inverse, if we take the function, we end up with f of x equals y. If we take the inverse, we go back to x. Evaluate it at f, go back to y. Take its inverse, go back to x. Just keeps going round and round and round. So we've already discussed one aspect of inverse functions, but we called it an inverse image. So now let's examine a bijective function g that maps from x to y as defined by the arrow diagram below. Note that a maps to 2, b to 3, c to 4, and d to 1. Let's represent g as a set of ordered pairs. So that's going from x to y. So g is the mapping that goes from x to y. And it is the ordered pair. Set of ordered pairs is, let's see here, A2, B3, C4, and D1. And now we also want to represent G inverse. Well, G inverse is going to send Y back to X. So in other words, we're going to send 1 back to D. We're going to send 2 back to A. We're going to send 3 back to B. And we're going to send 4 back to C. And that is our inverse, or G inverse. We're going to talk about inverses a little bit more in section 7.3.